Okay, so what is thermodynamics? See, the word thermo, right? Okay, comes from the word temperature. Thermo means temperature or heat. Heat. Jacinta also has joined. Okay, Jacinta has also joined. Good. So thermo basically means heat, and dynamics actually has to do with what? With the movement of heat actually. Okay, dynamics basically means movement actually. Okay, so why we have such a topic? Okay, because heat, I think you will understand or you will know, heat can move, right? Heat can propagate, heat can go from one body to which body? To another body. Heat can do so many things. Okay, let me just give you an example. What can heat do? Let me tell you. Okay, see, heat, as you know, right? Can you tell me what can heat do? What can heat do? The effects of heat.
Raise the temperature of a body.
Raise the temperature. Okay, agreed. Heat can raise the temperature. Then what else, guys? Or anything you want to talk about heat? Just talk about heat. Anything you
It
want to
flows
share
from
about?
it flows from one body to another.
It flows from one body. It flows from one body to another body. Yes, correct. Okay, one body to another body. Heat can flow from one body to another body. That is also correct. Yes. Increase the kinetic energy of the molecules. Yes, kinetic energy of molecules. Yes. Okay, because if you have gases, no, and it may be solids also. Okay, can you tell me different type of motion that we can have? The particles can have. I'll tell you. Okay, one is what?
A
Linear
vibratory
motion.
motion, linear
Linear
motion,
motion. Yes.
vibratory motion,
Vibratory motion. Yes.
rotational motion.
Yes, rotational motion. Rotational, very good. Okay, so say, so you know what, heat can, kinetic energy can be involved in any kind of motion. Okay, it doesn't have to be linear. No, kinetic energy is there in rotational motion, kinetic energy is there in linear motion, kinetic energy is also there in vibratory motion. Okay, so what the point is that heat can facilitate these motions. Okay, heat can produce linear motion, heat can produce what? Vibratory motion, and heat can also produce linear motion. Okay, basically heat is a form of energy, right? So heat is a form of energy. It can be converted into kinetic energy, and that is motion. I hope you understand what I said just now. Okay, so heat is a energy. It can be converted into kinetic energy, and that means it can make objects move with different kind of motions. Okay, so that is one of the thing. Anything else you want to talk about heat? Anything you feel like, just talk about heat. Anything, guys? Yes. Come on. You can do it. I'm sure you have some ideas about heat. Sahanas has joined, but I cannot see. Sahanas, we just started, okay, and we are talking about heat, okay, so you have not missed much, okay. Bajiruhan has left the meeting. Okay, guys, yes, anything else? Alright, you should tell me more things. Heat is measured in what units, guys? You can just tell me that also. Units of heat measurement is calories or
Joules.
joules. Okay, arcs also, of course. Okay, so we can have that. Those are the units. Okay, it is scalar or vector, guys. Heat, scalar quantity, doesn't need direction. Okay, so we have so many ideas about heat. Okay, now what is thermodynamics, right? So see, basically when we study how heat, okay, how heat undergoes transformation, how heat can produce many changes, okay, or interconversion of heat into other forms of energy, right? This branch of physics, we call it as what? Thermodynamics. Okay, so that is what you're going to study. Okay, it's not a very difficult topic. Okay, and you know what, mostly you will realize I will be talking about gases. Okay, it becomes easy for us to study gases and thermodynamics. Okay, we'll not talk about much here liquids, though we are not even going to talk, but gases we are going to talk, and we are going to talk about yeah, only gases. Okay, mostly. Okay, see, so there are few terms before we proceed. Okay, one by one I will talk about them. Okay, just see whether this makes sense or not. Okay, your concept has to be formed, then we can go to the main topics. Okay, see, the first idea is there is something called thermodynamic system. Now what is a thermodynamic system? Okay, see, try to understand this. Suppose if I have a container. Okay, I have a container. In this container, okay, we have lots of particles, gases. Okay, so these gases, okay, I can say that these are what? These gases are nothing but what? Assembly of
Atoms.
atoms or molecules, okay, or particles. Assembly of molecules or atoms or particles. And this assembly of particles, they have one very nice property, okay. Do you agree that these gases that I have drawn, okay, will their properties change or not if I supply them heat? Just ask yourself, can they gain heat or not? You can ask yourself that question also. Can they gain heat? Yes. Can they lose heat?
Yes, sir.
Yes, they can gain heat also. They can. So that means they can interact with heat. No, they can make use of heat. Okay. So these gases, right? It is an assembly of particles, and which can help in transformation of heat. Okay, transformation of heat, because you know why? The heat will be gained and the gases will have some motion because of that heat. Okay, their motion may change. Their kinetic energy may increase or may decrease. Okay, so whatever I'm saying, it has to do with the transformation of heat. The heat has been changed into kinetic energy. Okay, so who can do this? Who can take the heat and transform the heat? The gases can do it, right? So this assembly of particles which can transform heat, right? We call this assembly as what system, guys? Just now I told you what is the word. We call it thermodynamic system. Any assembly of particles which can gain heat and change its own properties, right? We can call it a thermodynamic system. Are you clear with this part, guys? I think this part is easy. Okay, so yeah, these gases are a thermodynamic system. Example, I can take hydrogen gas, I can take oxygen gas. All of them, they can take heat and they can change their properties. Okay, so they are called thermodynamic system. Okay, so yeah, one more thing. Every system, okay, is going to have certain value of pressure, certain value of volume, and certain value of what? Temperature. Let's come back to this example only. See, this system of gases, right? I think you'll agree with me, right? They will be at certain temperature. Yes, right now they have certain temperature. It cannot happen that we don't know about the temperature. Okay, they have certain temperature. These gases, they are going and hitting the walls of this container. So when they hit the walls of the container, the force experienced per unit force applied per unit area of this container, we call it pressure due to the gas, because the gas molecules are hitting the walls, so they apply pressure on the walls. And obviously these gas molecules, they occupy some volume. Okay, so this system, right, that we are talking about, the thermodynamic system, they are definitely going to have certain value of what? Temperature. They are going to have certain value of volume, and they are going to obviously have certain value of pressure. Okay, so that is a property of thermodynamic system. They always are going to have these properties like temperature, the volume, and the pressure. Okay, then what else we have? See, just now I explained to you, right, the pressure, the volume, and the temperature. Okay, these are known as thermodynamic state variables. The assembly of particles, right, is called system, but these properties like pressure, like volume and temperature, okay, we call them state variables. Now idea is why we call them variables is because you may understand the gas. What do you think? Will it have same temperature, or the temperature can change, guys? For a gas, temperature can change. Yes. Can the pressure of a gas change due to a gas change or not? Yes, the gas may be applying high pressure, the gas may be applying low pressure under different conditions. Okay, can the volume of the gas also change or not? Yes, the volume of a gas also may change. As a result of it, what I'm saying is the properties related to an assembly or a system, right, which can change, we call them what, guys? We call them state variables. Variables, I think you can understand now. Variables means what? You can change, right? Constant and variables. Constant doesn't change, variables they can change, no? So these are the things we can call them as variables. Volume can change, pressure can change, and temperature can change. Okay, I can give you an example. Okay, I can give you example here. Let's take this example. Okay, let's say I have a container fitted with a piston. Okay, and this piston can go up and down. So we have gases here also, you can see. So right now, obviously you will tell me right now, okay, this gas is certain pressure P1, it has certain volume pressure, volume V1, and that certain temperature T1. Okay, but you know what, I can do this. I can come and take this piston, apply force from outside, and the piston may appear here now. So you can easily understand now what is going to happen. If the piston is appearing here now, you tell me, we have the same volume or we have reduced the volume, guys?
Reduce
the
volume.
The volume has been reduced. Yes, the volume has been reduced. Okay, what do you think is going to affect? Is going to affect the pressure or not?
Yes, sir.
Okay, now the gas molecules are hitting the walls or hitting the walls more frequently.
More frequently.
The wall is so close now. See, the walls, the gas molecules are hitting the walls, no? But the walls are so close. Now the gas molecules will hit the walls more frequently. So the pressure can be increased. Okay, in that case. And what about temperature? If anybody can tell me,
It
we'll
will
have
increase.
we'll have collisions between them or more collisions between the molecules now.
More
collisions.
More collisions between the molecules. Okay, collision always results in the increase of temperature, no? So we have that top point also. Okay, so see, I just did something, right? I've changed the properties of this system. Okay, I've changed the pressure, I've changed the volume, I've changed the temperature. We can do that, and that's why all of these, right, we call them what, guys? We call them thermodynamic state variables. Okay, one thing more you should understand: when the piston was here, okay, it was in a state where the variables were P1, V1 and T1. Now when the piston is here, it is in a different state. The different state. Okay, and how do I know it is a different state? Because now it has different pressure, it has different volume and different temperature. Okay, the whole thing I can call it state A, and this whole thing I can call it state B of a gas. Okay, that means the properties of a gas has changed, so that means the state of a gas has also been changed. I think you understand the making. I think the name state, I think now makes sense, right? Is it okay? State. Do you understand the meaning of state, guys, now?
Yes, sir.
Okay, the gas was in this state, but when I applied pressure or force from outside, we have changed the properties. So now the gas is in a different state with these properties. Okay, the properties have changed. So now I'm going to say that the state A has been changed to which state? Now it is in a different state. The gas is in a state B now. Okay, so I hope little bit idea you got it. Okay, now that's why you see, okay, we have this. I do not know whether in chemistry you have done already or not. Have you done equation of state, guys, in chemistry by now? This formula here.
Yes, sir.
Yes,
Okay,
sir.
let me remind you what is this. Okay, see, first of all, let me remind you, okay, what is an ideal gas. So basically I'm talking about equation of a state, equation of an ideal gas, actually very important. Check. Okay, today is the day you have to learn this properly. Tell me whether it makes sense or not. Okay, say P is inversely proportional to volume. Do you agree with this one, guys? This means if the volume decreases, the pressure should increase. Okay, I think you know this as a law also, right? What is this law called?
Boyle's law, sir.
Boyle's law. Yes, very good. This is called Boyle's law. Okay, this will happen provided what is constant, guys? This temperature
Temperature is constant.
temperature is constant.
And
Okay.
the mass also, sir.
And the mass of the gas, okay, mass of the gas is also constant. Okay, so temperature should be constant, mass of the gas obviously, okay, going to remain constant. This is called Boyle's law, and it basically means what, you know, if just check not graph, I don't want to draw. Okay, basically it means this: if I have certain a gas enclosed in a container. Okay, we have already discussed this, but just an idea. And these molecules, they are going and hitting the walls. That's how we have pressure due to the gas, right? Okay, so they are hitting the walls, so we have pressure due to the gas. Now if I take the piston from here, okay, from here to here, just imagine. Now you tell me, okay, the gases will occupy same volume or more volume?
More volume.
More volume. The gases will occupy more volume. And more volume means, what do you think now? The gases will apply pressure or less pressure?
Less pressure.
Less pressure. So that's why they're inversely proportional. That is what is this law is all about. Okay, provided I don't change the temperature. Okay, okay. One more law is there. Okay, what is this called? P is directly proportional to temperature. Have you seen this one, guys?
Charles' law, sir.
Is this Charles' law, guys? Is this Charles' law, guys? Yes. Okay,
Yes,
Manba is
sir.
saying Charles' law. Okay, so this is Charles' law, right? What does it mean? You know, it means that if the volume is what? Not changed. If the volume is constant. Okay, let's do that also very quickly. Let me show you what does it mean. Okay, if the piston is back here, okay, I don't change the volume at all. But look at this. Don't change the volume. Think about this. Okay, but let's increase the temperature. How can I increase the temperature? I can heat it. No, heat. I give heat to the system. Now you tell me what will happen to the temperature. The temperature will remain same or increase?
Increase.
Increase. when the temperature increases, now you think and tell me, okay, will the molecule just sit like that, or it will add up, or it will go to the molecules and increase the kinetic energy?
Increase the kinetic energy.
Increase the kinetic energy. So now the molecules, they will go and apply force on the walls, or they'll apply more force on the walls, guys?
More force.
Yeah, that's why, okay, when we supply heat, it's like increasing the temperature, and temperature is known to affect the kinetic energy. Kinetic energy means they will increase the velocity with which they hit the walls, and as a result the pressure is going to increase. Okay, so that's why, look at this, it simply means if the temperature is increased, even the pressure due to a gas is going to be increased, directly proportional. Okay, now these two relations I'm going to combine. Okay, so when I combine, look how does it look like. Okay, but before I proceed, I should have told you what is an ideal gas. I did not tell you. I'll do it in a while. Okay, so if a gas is obeying what and what, you know, if a gas obeys which one? Boyle's law and what law?
Charles'
Prayas
law.
is also joining. Okay, if a gas is obeying these two laws, okay, then the gas is known as what gas, guys? It's known as
Ideal gas.
ideal gas. Another name is perfect gas. Okay, there are something more to it, I will discuss later, but for the time being, if a gas is obeying Boyle's law, if a gas is obeying Charles' law, we have to call the gas as ideal gas. Okay, so right now I'm going to combine both the equations, check how it's going to look like. Okay, pressure is found to be inversely proportional to volume and directly proportional to temperature. So from here I can write P is equal to some constant times T by V. Okay, and then I can multiply P and V is going to look like PV equals to some constant, and then I can write here T, and this constant, right, okay, is found to be N into R. Okay, I'll tell you what is this. This small n represents here number of moles, that's the constant, okay, one of the constant, and this R is universal gas constant. Okay, this has a value, right now I don't want to write, but just remember this. So we got an equation out of these two laws. Okay, that is your PV equals to some constant times temperature, and this constant, it is, I told you just now, is NR, where N is the number of moles and R is a universal gas constant. Okay, so I can write now PV equals to N into R into T. This equation is called perfect gas equation, please don't forget it, or this is also called ideal gas equation, and this is true. Okay, anytime you feel the gas is perfect gas or ideal gas, you can use this equation. Okay, so remember this, we are always going to be using this equation. Okay, PV equals to nRT, and the very nice thing about this is what, you know, check, if I tell you that pressure is P and the volume is V, then for a given mole of a gas the temperature will be fixed. Did you understand, guys, what did I say just now? What does it mean? If I tell you, okay, pressure is fixed, let's call it P1. If I tell you volume is also fixed, call V1, then the gas, certain mole of a gas does not have any other option but the temperature should be how much? T1. Did you understand what I said just now? I'll show you another one. If I tell you the pressure is P2 and the volume is what? V2, then what do you think, guys? NR. Can the temperature be T1 or cannot be T1, guys? What do you think for the same gas?
No, sir.
This cannot
Yes,
be
sir.
happening. Okay, this cannot be happening, right? Okay, but yeah, this also can happen. Okay, but what I'm trying to say is that for a given pressure and given volume, the temperature what is determined by given this equation. Okay, in this case I wanted to write T2, okay, but sometimes you will notice that T1 can also become equal to T2, so I should not go there. Okay, I'm confusing you right now, I know. Let me remove this part, okay, because something is there. Okay, but my point is this. Okay, see, if I tell you, okay, for a gas this much is the pressure, if I tell you this much is the volume, then automatically you will be able to tell me what, guys? You will be able to tell me using this equation
The temperature.
what is the temperature of the gas. That means at what temperature, at what volume, what will be the pressure. Though any one of them can be fixed. If I know two of them, I can know the third property automatically. Okay, that is what I wanted to tell you right now. Okay, so let me give you one more idea behind ideal gas, okay, or perfect gas, and then I think I can proceed. Okay, say, yeah, so just remember this one. What I want to tell you is that this is an equation I can always use, okay, where your N is the number of moles, yeah, N moles of a gas, and R is a universal gas constant, which is 8.314 joules per mole per Kelvin. Okay, And one more thing, when I'm using this equation, okay, your temperature has to be measured in absolute scales. That means Kelvin scale, okay. Remember this, you have to use Kelvin as your units, okay. So now see, now what is thermodynamic equilibrium? Okay, let's talk about this very quickly, not very difficult, okay. See, thermodynamic equilibrium or thermal equilibrium, okay. See, if there are two systems, okay, they have same temperature, this is good enough, okay. You don't have to check anything else. There are two systems, and if they have what, guys? Same temperature, then we say that the two systems are in what, guys? They are both in thermal equilibrium, okay. And the moment this happens, if the two systems are in thermal equilibrium, then their characteristics like your pressure, volume, temperature, mass and other things are not going to change, okay. Let me give an example. Say, suppose I have a system A, okay, and I have a system B, okay. These are molecules, these are particles, okay. These are also particles here, okay. These are maybe same particles or maybe different particles, okay. But you know what, I tell you that they have same temperature. The temperature of this is T1, even the temperature of this is T1. They have same temperature and they are joined, okay. You will notice that I have to say that the first system is in thermal equilibrium, okay. You can understand, it comes from the word, okay. Equilibrium means what? Nothing happens, right, in that system, okay. Whenever they use the word equilibrium, no, that means the system is not going to undergo changes, okay. So that's why what we are saying is what, if two systems are in thermal equilibrium, that means what? You tell me now, will they exchange heat or they will not exchange it, guys? What do you think?
They won't exchange
No
it,
exchange
sir.
of heat, no exchange, yes, no exchange of heat. This is not going to happen, right, because they have same temperature. How can they exchange heat? So we are going to say that they are in what equilibrium, guys? They are in thermal equilibrium. And if they are not exchanging heat, nothing much is happening, right? Then the properties of the system, right? Then the properties of the system, do you think it changes or does not change? Does not change. That is the meaning of what? Thermal equilibrium. Guys, is it okay what I said just now? What is the meaning of thermal equilibrium?
Yes,
Yes,
sir.
sir.
Okay, so is there a possibility that there can be more than two systems and all the three systems also can be in thermal equilibrium or not?
Yes, sir.
Yes, there can be another system which is in different or same temperature, guys. There can be a third system which is same temperature as what, guys? As system B and system A. Then also you will notice, right, they will not exchange heat, they will not exchange their properties, nothing much is going to happen, okay. And this condition, I'm going to say that A is in thermal equilibrium with C, A is in thermal equilibrium with B, and B is also in thermal equilibrium with C, okay. I think this part is quite easy, okay. So this is not so difficult, okay. Then this is a easy note here. I think you can understand this one. Say, an isolated system is always in what, guys? Thermal equilibrium, okay. Think about this. Can I tell you that there's an isolated system? This is an isolated system A, okay. There's nothing around it. Just imagine, nothing, okay, empty. Then what will I call it, guys? I'll call it system or isolated system. It is called isolated means to be alone, no? So isolated system, okay. So now you think and tell me, okay, can this system gain heat or cannot gain heat from anywhere?
Cannot gain heat.
It cannot gain heat. Can it lose heat or cannot lose heat?
Cannot lose heat.
Because it cannot do anything, right? It cannot gain heat, it cannot lose heat. So its temperature changes or doesn't change? Temperature cannot change, pressure cannot change, okay. Nothing can change, right, for this system, okay. So you tell me, will its properties change or will not change?
Will not change.
So can I call it an equilibrium or not? This is system is in equilibrium, okay. That's why this is written here, this short note, okay. I think you can make out that, okay. Now Zeroth law is very easy, okay, not very difficult. So let me tell you laws in thermodynamics, okay. There are three laws we are going to study. Thermodynamics, there are three laws. One is called Zeroth law. We don't have first law, okay. In Newton, though, we have first, second, third law. Gravitation also another we law have, right? But in the thermodynamics we have Zeroth law, zero, okay. Zeroth law. Then we have the first law, and then we have the second law. These three we have to study in your course, okay. So Zeroth law is very simple. I'll just quickly tell you what is this. Say, okay, Very, very simple, not difficult. If I tell you A, B are two systems, okay, and there's a third system called C, okay. The rule is very simple. If A and C are in thermal equilibrium, okay, look at this. A and C are in what? Thermal equilibrium, okay. And then somebody tells you even B and C, there are two systems, they are also in what, guys? Thermal equilibrium, right? So B and C are in thermal equilibrium, A and C also are in thermal equilibrium, okay. Then the Zeroth law, the first law that, right, that I'm talking about, says that even A and B will be in thermal equilibrium. Does it make sense? If A and C are not exchanging any heat, no exchange of heat, if B and C also not exchanging heat, then automatically what will you say, guys? Even A and B also must not exchange heat. So if A is in thermal equilibrium with C, B is in thermal equilibrium with C, then automatically what should happen, guys? Your A and B also should be in thermal equilibrium with each other, okay. Does it okay, this is the one, yeah, okay. I think you got the point, okay. So just check, we'll just read it very quickly. Check, okay, you have to read it, okay. If the thermodynamic systems A and B are separately in thermal equilibrium with a third system called C, then the systems A and B are also in what? Thermal equilibrium with each other. So this is really going to happen, okay. See, system A with system C in equilibrium, system B in equilibrium with again system C, then automatically then, okay, look at this, then even your A and B also must not exchange heat, okay. So I think this part is very, very easy. It's fine. Is it okay? Can I say that?
Yes, sir.
Okay.
Yes, sir.
And who determines, I told you, whether the systems are in equilibrium or not? Temperature. Who's it? Temperature. Just ask yourself if the systems are in equilibrium or not, okay. Or just ask yourself if the systems have same temperature or not. If the system they have same temperature, that means for sure they are in equilibrium. They will not exchange any heat, nothing like that, okay. So that is done for the time being, okay. Now let's talk about heat. I've already talked about internal energy, okay. So now something I have to talk about is very nice, okay. Let's talk about internal energy and perfect gas, okay. Let me just do it. Let me write this equation again. Say PV equals to N into R into T. This is called ideal gas equation or perfect gas equation. Now what is an ideal gas? Check, okay. There are many properties. I'll just talk few of them. What is an ideal gas? Check, okay. If I have a gas which I can imagine, okay, the gas particles or the gas molecules, the gas molecules are very, very tiny, okay, very, very tiny. So what kind of volume do they have, guys? What do you think? They have very big volume or negligible volume? Yes, I'm saying if, okay. If the gas molecules are what, guys? Very, very tiny, then their volume is what? Negligible. Negligible or, yeah, negligible compared to what? This is the volume occupied by the whole gas, okay, suppose, no? Then you know what? This volume occupied by the entire gas, not of individual molecules, okay, the volume occupied by the entire gas, okay. If the volume occupied by the entire gas is so large, okay, and the volume of each gas molecules can be what? Can be neglected. Then I have to say that, yeah, the gas may be what gas, guys? Ideal gas. So this is first property, okay. The gas molecules are big or very, very tiny. Ask yourself, what are we talking about? Yeah, we are talking about ideal gas, okay. Yes, okay. So if we are talking about ideal gas and you see that the gas molecules are very, very tiny, then what are we going to say? This gas must be maybe an what gas? It may be an ideal gas, okay. That's first thing. Second thing, okay, I'm not going to talk all of them, just one more topic, okay. Look at this, okay. Suppose this molecule, this is a gas molecule and it is moving, okay, and this another gas, same molecule, okay, and it is moving in this direction. Notice and tell me, okay, tell me, will they collide or not? Right,
Yes,
now,
sir.
will they collide? No, one is going here, no?
Oh, no, sir.
No, one will go here, right? Yes, okay, one will go here and one will go here, no? So they collide or not collide?
Not collide.
So can they apply force or not on each other?
You cannot.
They cannot apply. Okay, but notice something. Okay, do you know that gas molecules are made of protons and electrons, right? Or any atom, right? Any atom is made of what? Protons and electrons, the positive charge particle and the negative charge particle. So this gas molecule also will have positive and what? Negative
Negative.
charge particles. And you know what, sometimes this happens. See, if the gas molecules are close, okay, if the gas molecules are close, moving close to each other, you know what happened? Without colliding, without what, guys? Even colliding, they can apply what?
Force.
Force on each other. And this is called what? When you apply force on each other, right? Because of your position, you are very close, right? This force results in an energy called what energy, guys? Potential. Do you know this one?
Potential energy.
Without touching, okay, there's a force being applied, no, because of the position. Okay, I'll give you another example. Look here, I think I made you confused, so I'll just fix the things right now. Please listen, you will understand. Okay, imagine this gas molecule is just moving close to another gas molecule. Okay, they are not going to hit each other, and we notice that the force they apply is also how much? Is 0. So now you tell me, okay, this is the position of the gas, this is the position of the second gas, okay, position A and position B. Tell me, do they apply any force or no force between them? No attractive force, no repulsive force. Okay, if this is going to happen, then I am going to say that your gas is what gas?
Perfect gas.
If the force between them is what? 0.
Zero.
When the gas molecules are in which position? Position A and position B, very close to each other, by the way. Okay, very close. Okay, and you know what, as a result, what is the potential energy right now? What are you going to say? Your potential energy is going to be equal to how much, guys?
0.
0. Can you understand? Potential energy is because of position. If there is no force involved on these positions, then your potential energy has to be also called equal to how much, guys? It is 0. Okay, then, okay, let me ask you like this now. Okay, so this is a property. Okay, remember, this is a property of which gas, guys? Perfect gas.
Ideal.
So, ideal gas or perfect gas. Okay, do they have any force of attraction? No. Do they have any force of repulsion? No. Even if the two gas molecules are very close to each other, they are not going to apply any force of attraction or any force of repulsion. Okay, but okay, a real gas is different. Real means a real gas. Okay, perfect gas is actually it's a name given to a gas, okay, which has these properties, but perfect gas is not a real gas. Do you understand the meaning of difference between the naming, guys? What do you think real gas is, guys?
Sir, it exists.
Yeah, real gas, they really exist. What about perfect gas?
No gas is a
No
perfect.
gas is perfect gas. Okay, but gases can behave like what? Gases can behave like the real gases. Okay, I'm repeating, real gases can behave like what gas, guys? Perfect gas under certain conditions. Right now that is also not important. Okay, but just to proceed, okay, this is the most simplest thing we can talk about. Remember, in a real gas, if a gas particle is moving, okay, if there's another particle moving, okay, then you know what, there will be certain amount of what? Force of attraction between the molecules, or maybe what? Force of repulsion between the molecules, even without touching each other. Okay, just they pass, they just have to pass very close to each other. Can you understand what I said just now, guys? They just pass too close to each other and they will apply force on each other, a force of attraction or maybe repulsion. As a result, you can tell me the potential energy will be 0 or not 0, guys, in this case? Yes,
Not
yes,
0.
not 0. Okay, did everyone understand what I'm trying to say? If you didn't understand much, just remember this. In a perfect gas or ideal gas, what is the force between the molecules, guys? It is 0 or not 0? The force is 0.
0.
And the potential energy is also 0. But for a real gas, there's really a force between the molecules which really exists, okay, and the potential energy between them is not 0. Okay, can I proceed with this much concept, guys? Because what is an ideal gas, I just tried to explain to you a little bit of it. Yes,
Yes,
yes.
sir.
Okay. Anybody has doubts here? If I ask you what's an ideal gas? Okay, what's an ideal gas? Very quickly, recap. What's an ideal gas or perfect gas, guys? Quickly.
A gas which follows Boyle's law,
Yes,
Charles'
a
law, sir.
Boyle's law, if it is obeys, very good. And which also obeys?
Okay.
Charles' law,
Charles'
very
law.
good. Yes, what else is the property? Some other property,
Uh,
this is correct. The volume of the
Potential
gas.
energy is
Okay, potential
Viscosity.
energy between the gas molecules is how much? Zero. The
Zero.
force of attraction between them is almost how much?
Zero.
The volume occupied by these gases is how much? Zero. Negligible. Yeah, almost zero. Yes. Okay. So these are the properties of an ideal gas or a perfect gas. Okay. Now let me come back to this one. See. So all this time, okay, I took so much time to explain just this part, but now comes why we need this thing. See, we have something called internal energy of a system. Okay, don't worry. See, I'm just explaining you only few concepts here right now today. Next day, okay, we will do much better, much more bigger things. For now, we're just forming concepts. Okay, so what is internal energy of a system? Okay, internal energy definition is very simple: the total energy possessed by the system due to molecular motion and molecular configuration. Okay, when I say motion, it means what? Molecular kinetic energy, and molecular configuration means position. Actually, that means potential energy actually. Okay, so that basically means the sum of what energy? The kinetic energy and potential energy. When you take the total of kinetic energy and what energy, guys? Potential energy, basically this only, right? That is known as what, guys? Internal energy of a system.
Energy.
Yeah, internal energy of a system. Okay, so now check the kinetic energy, right? A system can possess, I told you at the beginning, there are three types of kinetic energy we can have, right? Translational, rotational, and obviously vibrational. Okay, but you cannot say there is vibrational potential energy, translational potential energy, rotational that is wrong, totally wrong. Okay, so just check the definition here. So internal energy is nothing but what, guys? I told you, sum of kinetic energy and potential energy. Okay, you can write UK, UP, and U is the symbol for your internal energy. Okay, now check something we have learned just now. For an ideal gas, for a perfect gas, which one is zero, guys? What is zero for a perfect gas?
potential energy.
Potential energy is equal to zero. This one is zero, right? That means internal energy for an ideal gas. Okay, what am I writing? Internal energy, internal energy for an ideal gas is nothing but equal to which energy, guys?
Kinetic energy.
Only kinetic energy. Okay, and here I have made a mistake here. See, so what is zero here? UK 0, UP 0. UP. So when I give you this notes, no, please check. Okay, so potential energy is 0. That means for an ideal gas, the internal energy is nothing but equal to what energy, guys? Only kinetic energy. Okay, no need to talk about potential energy. I think this part is clear. Is it okay? Yes.
Yes, sir.
Okay.
Yes, sir.
Now check. All of you are clear with this, whatever I'm doing today. I'm sure. Okay. So now check. See, notice something. Okay. And I told you something earlier, right? Okay. Or maybe let's say we will prove it later. Your kinetic energy is found to be totally dependent on temperature. I'm repeating again, What is found to be totally dependent on temperature, guys? Your kinetic energy is found to be totally dependent on temperature. Does it make sense? High temperature means what? Gas will move fast or much faster? Much faster. Yes. Okay. So that is basic meaning of this. No, much more temperature means much more kinetic energy. And just now I showed you, right, the internal energy of a perfect gas is nothing but entirely what energy? Kinetic energy. So if I ask you, okay, for a perfect gas or a ideal gas, what does your internal energy depends upon? Can I say internal energy depends totally on temperature or not? Your internal energy depends totally on temperature. Why? Because internal energy for a perfect gas is nothing but what energy, guys? Kinetic energy. And kinetic energy totally depends on what? Temperature. That means indirectly I'm saying internal energy depends upon
Temperature.
Temperature. Okay, so please remember this, okay, because this will come handy later on for us. Okay, I think you are following me till now. Then I'm done talking about this. Okay, quasi-static process is, I will tell you what is this, but I think not very important. Imagine, okay, a system looks like this with properties P1, V1 and T1. This is a system and I look at the system. Okay, I keep looking at the system. Okay, and you know what, it doesn't look like as if there's a change in the, looks like there's no change in the system. Okay, but actually to say there are very little changes, suppose very little, or let's say very small amount of changes. There are changes, but there are very small amount of changes, so let's say they're very slow change, very slow change taking place in the system. Okay, suppose, then you know what, I have to say that the change that is happening in the system, right, which is so slow, right, okay, that change we are going to call it what, guys? Quasi-static process. Okay, static, I think you can understand, it looks like as if it is, everything is at what?
Rest.
Okay,
Rest.
and quasi, I don't know, I think quasi basically means very slow. Okay, I don't know what is the meaning of quasi. Anybody knows what is the meaning of quasi? I don't know what is that. So think about quasi-static process like this. Okay, see, you look at the gases right now, and then you look after 2 hours. Okay, and you see that nothing has changed. Okay, do you agree, guys, that there may be few changes in the gas or not? If you just look after 2 hours, it looks like nothing has changed, but very little change may have occurred, right, which you cannot even record. Can you understand, guys, what I'm trying to say? This can happen, right? Maybe a very slight change of temperature which you cannot even record. Okay, so that change, right, we will call it what process, guys? We'll call it
Quasi-static.
static process. Okay, something has happened, okay, but very small amount and very slowly, so that very little change, right, we call it quasi-static process. Okay, don't worry about this, not very important, but the next, this is important, very important. See, okay, I'll only talk about this, after this I'll stop. I told you every whole week, okay, we'll try to meet every now and then, but we will do only for 1 hour. Okay, but we will try to give full attention for this 1 hour. I'm telling you, huh? Next day also you have guys have to attend, huh? I'm telling you, cannot be absent. Yes. Okay, so see, okay, so a process means basically you are doing something. Okay, when you do something, right, we call it a process. When you try to bring some changes, right, we call it a process. So there are different types of process when we talk about. Okay, imagine you have a gas and you want to bring some changes, no? So that will be known as a process. Okay, now you can bring the changes in different ways. Okay, look at this, you can bring the changes, but you can keep the temperature what, guys? Constant. Okay, you can bring the changes, so we'll call it a process, but you try to keep the temperature what? Constant. Then this process we have to call it what, guys? Isothermal process. Can you understand this, what I said just now, guys? Imagine a gas. Okay, look at this. Okay, this can happen. Okay, don't think this cannot happen. Okay, this can happen. You have a gas. Okay, I'll not give you the details. Okay, the piston has been pulled from here to here, see. So you tell me now, is it what is this a process or not, guys? The piston has gone from here to here. Okay, so what will I call it, guys? Is this a process or not?
Yes.
Ask yourself, what are the things which have changed here right now? Something has definitely changed.
Volume,
Volume has definitely changed.
Changed.
There's a change in volume, correct?
pressure,
Pressure may have changed or may not have changed. Okay, till now I did not tell you, but I'm telling you something. I'm telling you temperature is not changing. Temperature is constant. Suppose temperature is what, guys?
Constant.
Constant. That means you started with some 0 Kelvin, then automatically what happens? Not 0 Kelvin, very bad temperature. 10 Kelvin, okay, or let's say 100 Kelvin, doesn't matter, but you have same temperature. Okay, as the piston has gone from here to here, the temperature did not change, but definitely something has changed. What is that?
Volume.
Volume has changed, temperature did not change. What do you think will happen to pressure, guys? What will happen to pressure? Pressure will increase or decrease?
Increase.
Pressure will
Decrease.
decrease. Yes, and that is what you have learned your law, right? Pressure is inversely proportional to what? Volume when the temperature is
Constant.
constant. Okay, and I'm going to show you a graph for that. Okay, just give me some time. But the point is this. Okay, do you understand first of all why the pressure decreases? First of all, tell me why the pressure decreases. Yes, yes, yes. Why does the pressure decreases? Yes, yes. Okay,
Due to
because
increase in volume.
due to increase in volume, now the molecules, what do you think? They're moving faster or moving at same speed? What do you think?
Same speed.
The molecules are moving at same speed. Do you agree, guys? Because the temperature is same,
Constant.
constant.
Yes, sir.
Temperature is
Constant.
constant. So they have kinetic energy or less kinetic energy or constant kinetic energy?
Constant kinetic.
Constant
Constant
kinetic energy.
kinetic energy. That means, will they go and hit the walls or they'll hit the walls less often now?
Less often.
Less often. Okay, my spelling of less is very deadly. Okay, so see, less often. So automatically the pressure has to what?
Decrease.
Decrease. Okay, so I think you agree with this one, right? Okay, okay, one more thing. Okay, do you agree that if I would have increased the temperature here in this case only, okay, I have increased the volume also, and I've increased the what, guys? I have increased the volume also. Suppose I'm just talking, okay, a bit more. Okay, if I increase the volume and I increase the temperature also, tell me, the pressure has to fall or pressure can remain constant? What do you think?
Pressure will be constant.
Pressure can remain. Okay, pressure can remain. Yes, pressure can remain constant if I increase what and what, guys?
Volume and temperature.
Volume and temperature.
Sir,
But
kinetic energy won't be constant, right?
kinetic energy won't be constant, no. But pressure is not only due to one molecule. Do you realize? Will pressure be due to only one molecule, or you have to take into account the collision from all the molecules? Did you understand what I'm trying to say? What you are saying is, because the temperature is increased, the kinetic energy also increase, right?
Increase.
This is what you want to say, right? So you want to say there should be more pressure, right? Is that what you want to say, Abhishek? Yes, yes.
No, sir.
Okay, then what do you want to say? Tell me, tell me.
Sir, I just meant that temperature increase, so kinetic energy should increase.
Okay, okay. After that, you don't want to say anything, right? Okay, you just want to say till there. Okay, fine. Then I'll not go into what I wanted to explain. Okay, I'll not go there. Okay, but okay, I think I'm done. Okay, so please tell me, guys. Okay, okay. So, did you understand that the volume was changing? Yes, you saw that the volume was changing and the pressure was decreasing, but temperature is kept constant. This can happen. Okay, so we call it what? Isothermal process. Okay, in this case right now, you know what will I call it? I will call it isothermal expansion. Okay, that's the word we use. I think you can understand why we call it expansion, right? Same thing can happen, right? The piston can be taken from here and can be brought till here. Okay, and you know what? We don't change the temperature. That can also happen. Okay, later I'll talk into detail. Okay, so now what has happened? Tell me, guys. The volume is same or volume is decreased? The volume has decreased. What about the pressure, guys? What do you think? If temperature is constant, pressure will increase. Still inversely proportional, but this time I'll call it isothermal expansion, or I will call it isothermal compression. Isothermal compression. Okay, decrease in volume without the change of temperature. This can happen. Okay, I will show you later. Okay, then I'll see. What about the next process, guys? I have another 5 minutes. I'll do it. Okay, finish this part. See, adiabatic. This also can happen. Okay, there is no exchange of heat. No exchange of heat. And you know what? The gas can change its pressure and volume and temperature. I'll give an example. See, okay. Look at this. Okay, think about this, okay, check. Okay, there is no heat coming and there's no heat going to come out from the system. Okay, there's no heat going to enter the system or come out of the system. Okay, now we have these gas molecules. Okay, Now think and tell me, think. Okay, I take this piston from here to here. Ask yourself, okay, when the piston, okay, let me just bring it back 1 second. When the piston is here, okay, let me just copy this quickly. This is important, okay guys, so that you get the concept. Okay, think about like this. See, if the piston is here, the pressure is P1, let's say the volume is V1, temperature is T1. There is no heat entering the system, no heat, okay, and no heat will leave the system, 0. Okay, think and tell me, okay, what will happen now? Check, okay, the piston, I take it from here to now here. Please think and tell me what will happen to the gases, guys. Do you think the gases are becoming faster or not becoming faster? That's the first question. Are the gases becoming faster or not becoming faster?
Not becoming
Not
faster.
becoming fast.
They're not becoming faster. The kinetic energy changes or doesn't change?
Doesn't change.
Okay, doesn't increase. Let's say doesn't increase. Okay, does not increase. No, cannot increase. Okay, but think like this now. Okay, say if the molecules now, okay, the gas molecules will go still and go hit the walls or not?
Yes.
They'll go and hit the walls. So what will happen now? Pressure will be same or pressure will decrease?
Pressure will decrease.
Pressure will decrease, and volume is definitely what, guys?
Increase.
Volume is increasing, pressure is decreasing. Okay, now think and tell me, what kind of collisions are we going to have between the molecules? Is there be frequent collisions or less frequent collisions?
Less frequent collisions.
Less frequent collisions, as a result of which what will happen? The gas molecules, yes, the gas is, yes, you said something?
Something.
Giovanna's saying, right, the gas will lose heat, right? No, Giovanna wanted to say something like that, right?
I'm not sure.
Okay, but you realize we are talking about you cannot lose heat, no? Okay.
Yes, sir, that's why I took
Yeah,
it back.
yeah, that's why you stopped. Okay, I know. Okay, now see, now look at this. Okay, if the gas molecules, they cannot lose heat to the surroundings, but do you agree with me that the gas molecules are losing energy by pushing the piston or not? Gas
Yes, sir.
molecules are losing energy by what? By pushing the piston. Do you agree with me that the gas is losing its kinetic energy or not? Or internal energy? Let me ask you like that, guys. Okay, by the way, why the piston is going here from here to here? Because
The gas is pushing it.
because the gas is pushing the piston, no? Otherwise, okay, don't think I brought the piston there, okay? It is the gases which are pushing the piston, no? So my question to you is, if the gases are pushing the piston, okay, and they don't receive any heat from outside, what will happen to the internal energy, guys? Will they be same, or they will reduce, or they'll lose their internal energy?
So it'll be the same.
They have to lose, no? Because they're pushing, right?
Oh, yes, sir.
When you push a door also, right, you're losing your energy, no? So these gases are also pushing the piston, right? So my point is this, okay, the internal energy remains same or changes? Changes. So now you tell me, the temperature will remain same or decrease?
Decrease.
The temperature has to decrease. Okay, all I want to tell you is this. Tell me now, will the pressure fall or fall very, very fast? What do you think?
Fall very fast.
Because the kinetic energy of the molecules is decreasing. Temperature is falling. So pressure cannot be maintained at all. So pressure is going to fall very fast. Okay, this is a process, right? We call it what process?
Adiabatic
process. Okay, I'm repeating again very quickly. Okay, say. Okay, very quickly. Okay, just listen, and I think you'll understand. Then I'll go back to isothermal again if you have problem. Okay, I think you're not so clear with isothermal, so just check. Okay, say the piston was here. Suppose I tell you the gas molecules have not gained any energy from outside. They have not gained any energy from outside, but you see that the piston has gone from this position to this position. So now ask me, I'll ask you, okay, the piston is reached from here to here. Who is pushing the piston, guys? The gas molecules are pushing the piston.
Piston.
Okay. Did they receive any energy from outside to do this, or they have used their own energy?
Use their own energy. kinetic
Adiabatic process, yes, they have used their own energy. So what will happen, guys? They'll have same kinetic and same internal energy or decrease internal energy.
Decrease.
Decrease internal energy means temperature will remain or it will lower.
Temperature will be.
Temperature will be lowered, okay? And what will happen to your pressure? What do you think? When the temperature lowers and volume increases, just imagine, very very sad case for a gas, no? Temperature is also low and the volume is also increased. The pressure cannot be maintained. It will decrease or decrease very very fast.
Decrease very fast.
Decrease very very fast. Okay. At this point, I want to ask all of you. Okay, all of you, please respond. Okay, guys, are you clear what I said just now?
Yes, sir.
Okay, Giovanna
Yes,
is
sir.
clear. What about Sangam? Sangam is clear. Caesar. Daxway is clear. Manbha is clear. Sure. What I'm saying.
Yes, sir.
Okay, Aisha is there. Ronika is there.
Yes, sir.
Okay. I want to show you now. Check. Okay. If it's not clear, please ask me. I want to show you one more thing. Okay, just that, and then I'm done. See. Then we will stop. Okay. Everybody happy. Okay, because it will not be. Okay. All of you are saying yes. So nice. Okay. So check now. Okay. Look at this gas now. I'll go back to isothermal. What process is this? Isothermal. Okay. Look at this piston. And look at this gas. Same gas. Okay. The piston reaches from this position to this position, okay, from here to here. Do you agree again it is expansion or not? Check. It is again what, guys? Expansion, okay. Do you agree that the piston has been pushed by the gases or not? Yes, tell me, guys.
Yes, sir.
Expansion, you agree, yes. Piston is pushed by whom?
The gas.
By the gases, yes, okay, correct. Okay. I don't want the temperature to what? I don't want temperature to what?
To fall.
Fall. Because it is what process?
Isothermal.
Okay. So you know what? Don't worry. The energy can come from outside now. Maybe you just heat a gas here, see? Okay. Now the energy which is coming into the gas, right, is helping it to maintain what? Is helping to maintain what? Temperature. So now the temperature is what? Going to fall or not going to fall?
Not going to fall.
Because this because this energy which enters the system, right, is helping the gases to push the what? Piston. And the gas is not going to use up its own internal what? Energy. The gas is not going to lose its own kinetic energy. That's why it can maintain what? Maintain
It's
temperature. Is not going to fall at all. Can you understand this? And now you tell me, will the pressure fall or pressure will fall slowly? Pressure will fall. Fast or slowly, guys?
Slowly.
Why slowly, guys? Did you understand why slowly? Yes, this is the question I want to ask you. Because now what do you think? The gases are losing their internal energy or not losing their internal energy?
Not losing.
The gases now are not losing their internal energy. The gases are not losing the temperature. The gases are not losing their kinetic energy in pushing the piston. Because energy is coming from where? Outside. Can you understand? So temperature can be maintained and the pressure also will not fall very fast. It will fall slowly. This kind of process is called what process, guys? We call it what? Isothermal expansion.
Isothermic.
Yeah. And the other one is called what, guys?
Adiabatic.
Adiabatic expansion. I'll give you an example. I'll give you a very good example. Okay, this is whose cycle it is. This is Rajdeep's cycle. Okay, Rajdeep is there. Okay, I just drew a tire. Okay, Rajdeep, I don't know whether he's there or not. Okay, but still, okay, let's take him to an example. No, imagine the tire, right, suddenly bursts. No, then all the gases will escape from here or not, guys? What do you think? The tire is bursting, okay. I don't know my diagram makes sense or not, but gases, what do you think, guys? The gases are occupying the same volume or they are expanding?
They're expanding.
They are expanding.
This is an expansion, right? Agree or not, all of you?
Yes, sir.
Okay, so this is an expansion. Okay, what do you think it is? Okay, he did not join because of bad internet connection. Okay, my point is this an expansion? Yes, you agree this is an expansion. Okay, is it isothermal or not isothermal? What do you think? Is it isothermal or not? Okay, forget about isothermal. Let me ask you a question. Can I call it adiabatic or not? Let me ask you directly. I'll tell you, this is an adiabatic process. You know why? Because did you realize that the gas will be expanding, okay, in a very big time or very short time?
Short time.
Very short time. The gas will expand in very short time. So within that short time, the heat will enter the system or leave the system, or nothing will happen. Or can I just ignore the heat part? It is, this expansion is not because of heat. I think you'll agree with me, right? This expansion of gas, right, is because of bursting, no? Because of so much tire pressure, no? It is not because of heat coming or leaving. Okay, so this is not going to be a very long process. It's a very short process. Okay, so mic, Giovanna, your mic. Okay, so now say so it is going to happen in a very short time without the exchange of heat. And you tell me, what happens to the pressure inside this tube now? It will be same or it will fall very fast?
Fall very fast.
Have you seen it gone? No, you know the sound also, right? The whoosh, right? It's to make, so the pressure decreases or pressure decreases very fast.
Very fast.
Pressure
Okay,
decreases
yeah.
very-
So whenever pressure decreases very fast, right, you can immediately come and say it must be what kind of process, guys?
Adiabatic.
Adiabatic process. If okay, heat was involved, if heat was still there and the gas is still trying to escape, what do you think? The pressure will decrease or decrease slowly, guys? Heat is coming inside the tire, okay? Right. The pressure will decrease slowly. Can you make out? Can you visualize? If you heat the tire and let the tire just burst also like that, okay, but if you keep heating the tire, you know what will happen? The pressure will decrease, but slowly, because the gases will be so fast colliding with the tire, and still it will maintain the tire pressure, okay. But some ideas at least you got. So I just want to show you one last thing, okay. 9:07 already, you know, I said till 9, but don't worry, I'll just quickly come back to this. There are two more processes very quickly. Let me tell you. Isobaric. Baric means bar comes from pressure. If the pressure is constant and you change other things. Isochoric, you change other things but you keep the volume. What, guys? You keep the volume constant but you change other things, okay. And isobaric means you change other things but you keep the pressure constant, okay. So such process will be called this and this, okay. So these are four processes. I'll send you the notes today only. Something you should understand. This PV indicator diagram I'll talk about next day, not today, okay. I'm done for today, huh? So you guys will get bored, otherwise you will not attend the next class, I know, if I bore you. So next day we will talk about this indicator diagram, okay. For today we'll stop, okay. So bye bye, thank you. Anything you want to ask, guys?
So tomorrow's class?
Tomorrow